Hello, hello. Welcome to our Menlo Community Call. So we're very excited to have you all here with us today. I'm Mimi, and I'll be your host for today. So before we get into things, I do want to mention something. We've made so many changes in the past week that we actually decided that these calls need to happen more often. So starting now, this is officially a weekly thing instead of bi-weekly. And of course, if you can't catch us live, that's totally fine. You can always rewatch the stream in your own time over on YouTube. So for anyone who's new to these calls, here's a quick rundown of how things usually go for us. So our team does their best to walk through the three main things every session: what we did to make Asimov better, what problem we ran into along the way, and how we solved it, if we did. So here's what today looks like. We'll be kicking things off with software, moving into hardware after that. Then we'll get into updates on the fulfillment side, then updates from our brain team, and then we'll wrap up with career opportunities towards the end. So we have lots of good stuff to get through today, but before we jump into it, we have a really big update that we wanted to share with you guys, and this is actually what got all of us buzzing here at Menlo. So we are shipping our first Asimov 1 batches very, very soon. Some of you may have already seen the email we sent out. It's generally been such a busy and exciting week for the whole team, and we're in the final stages of the production run right now. And here's the part that we're actually very excited to highlight. We'll be shipping the robot in groups of 10s. So it means that everyone who purchased Asimov is going to be building together as a group at the same time on Discord. So if you're not going to be if you're a little bit nervous or worried about this, you're not going to be doing this on your own. You're doing it alongside with other people who are as excited and interested in humanoid robotics as you are. And we think that's pretty special, right? So we'll have a lot more updates coming your way very, very soon over the next few weeks. So definitely keep an eye out on our Discord and X, and keep checking your inbox too. So with that, let's actually get started. Over to the software team.
Okay, I think for the software team, hi everyone, my name's Long, and I'm one of the engineers in the software team. So in the past few weeks, we have been quietly setting up like the platform so that later on, during the shipment of the Asimov, you guys can control and then connect your robots to the platform. But in the meantime, like while we are setting things up, we have prepared some of the um, simulations so that you guys can try out the Asimov online, like using the same locomotion that we have been training, and as well as just test drive it in some of the scenes that we have prepared. So this one is we have a version that is already live. You guys can try at the moment in try.menlo.ai. But I'm going to show you guys like the newest version yet, like the one that we will be pushing out next week, so that you can get a glimpse of what you guys can play with it. So you can connect with your Google accounts, and then when you get into the try.menlo.ai, you should be able to use the Asimov robot within different scenes. And the key thing about these scenes is that not only can you drive the robot in the scenes, but you can use our SDK, which will be compatible with the actual robot when we ship, and try it out on the simulation itself. So right now I've loaded up a scene. Right now it's a warehouse scene. So what you can do is that right now you can try to control the robots by doing WASD. Very simple stuff. And also you can also do teleoperation on the hand. So let me give you an example. So if I select this one and I try to move the joints, you can see that the joints actually moves. Okay, let me select another one. Okay. And okay, also you guys can control the robots with the SDK. So how do you guys do it? The way you guys do it is that first you guys need to get API key. Get API key. That's key. And then later on, You guys can use our quick start guide, which we have in the docs side. So you can go to the docs by visiting here, read the quick start, and then it's actually here. And then you guys can go through the installation guides, and then you guys can try it out. But later on, we'll be having features so that we can support you, so that you can try the Python SDK directly on the sites, but it's not ready yet. So right now, I prepared like a simple notebook so that we can all go through the flow. So then I can paste in the tokens, so I can run it and then try to connect the robots. Okay, and then this will be this piece of code will try to find the session that we are already on. Okay, no last session. Okay, I have to open the scene first. Give it a bit of a few seconds. Yep, we are here. And then you can try to connect to the SDK. Yep, you can see that we are in the scene warehouse. And then you can attach it. All right, it's up. So right now I'm just going to try very simple stuff, just moving the robots around. Yep, as you can see. So you can control the robots with, right now we're exposing a few commands. We can control the upper bodies as well as the velocity. And then you can also take the screenshot. Like this is the what you guys can see right here. Will be given to the to whatever through the SDK, and you guys can see it both from the top-down view as well as the view of the robots. Okay, so like in this, what we have already do is that instead of like doing a simple module rendering, as you can see, it's very responsive. We are actually doing the rendering on the client itself. But the module core physics is a simulation that we're using. It's on the backend side. So one cool thing you can do is that it's because all the rendering are done on the front end side. You can actually change the skins of the robots, like just by applying a new, like a new assets on top of it, without having to re-render the entire scenes. So later on, like we will be supporting like changing the scenes as well as changing like the assets inside here. So it gives us more potential on what we can do with the sim, so that you guys can have like a more realistic view or like try to play things out. Okay. One more thing I want to show is that I think this one looks pretty cool. Like I was the one setting this one up, and I think like like during the World Cup time, like I just think like what is one of the things that like the Asimov robot can do? I think it's that okay, this one, right? We can use very simple stuff, operation control, and then we can kick the ball inside the goal. And I think like, it gives me like a good demo effect on like how you can control the Asimov as well as how the scene looks and how like coherently like how it looks entirely within the scenes. Okay, you can change the skin. Yeah, to me it looks pretty cool. I'm not sure what you guys think, but to me it looks pretty cool. Okay, I think that's it on my side. Do anyone have any questions? Anything I can answer? Okay, to load custom scenes, we are using Mujiko like as our rendering framework and physics framework, and we'll be having what is called a hub and okay, I'm not sure if I should say this early, but we are still spinning things up so that you can not only update the scenes, but you can also update your own locomotion, and as well as like we will be supporting a training platform. So you guys can push your assets and then have it render and test things out yourself. Open source, we have not decided on the open sourceness of it yet, but I'm not sure on that side at the moment. So right now, so going forward, you should be expecting that it should be running on our platform first. Open source will be announced later if we decide to do. Yeah, it's the same one. I think like we have done a lot of like updates as well as iterations so that it looks better as well as and also make the scene look smoother. As you can see, the startup time is very good. So we have done a lot of optimization on that side too.
I think we lost Long for a second there, but we
What?
have another question. Maybe Yuki can take it.
Yeah, I'm not sure what is URDF. Yuki, can you help?
Thing that Visual Code can load, but regarding the rendering, it's actually just normal GLB file as you would have it on most game engine because it's just rendered with 3JS. Yeah.
Okay, please continue dropping your questions into the chat, but I think in the interest of time, we can move on to the next person.
Thanks, everyone.
Hi everyone. My first time being here, so a little bit nervous. So my name is James from the software team, and today I'm very excited to share with you one of our work stream that we are working in the background. At Menlo, we are very, very serious about robot safety and security. So this is why we are proposing a new robot authentication and security protocol or standard. The reason is because we think that like robot need its own security model. This is not similar to when you lost a phone. But if a robot is compromised, it can cause physical harm because it's operate in a physical space. Compared to a normal IoT or cloud security model, it usually start with trusting the cloud, but we want to flip that. We want the core idea is that the robot is the authority, and the cloud is only the replay, so that even if attacker cannot move the robot. The key takeaway of this. So instead of like using normal API keys, etc., we are using cryptographic key to ensure that the robot can verify that the command coming from the approved controllers, and the trust chain starting from the organization to user to device and to section, and the section key which sign a command with the robot itself can verify, and any relay server in between cannot fork any command. Yeah, that is key takeaway that we want. Yeah, and so for the next step, we are going to publish this to get a wider feedback from the community. We share more on the Discord channel. If anyone interested in learning more or want to take a look, please reach out to us on the Discord. Yeah. I guess that's all for me to share today. Yeah, not sure if anyone have any question.
Thank you, James. If you guys have any questions or comments on what James has shared, leave us in the questions in the chat. Otherwise, we'll move on to the hardware team next. Oh, I'm so sorry. I think Yuki. That's my bad.
Hi everyone, hope you all can hear me. It's nice to meet everyone across all the stream. My name is Yuki. I'm right now working as the developer relation and partnership at Menlo, but also one of the engineer that's trying hard to make sure that Asimov V1 will be available to the community soon and arrive at your doorstep within the shortest time possible. Right. Well, today I would like to show you guys one of our proudest achievement at Menlo. The first one is definitely Asimov, right? But the second one is actually our manuals. So we are working really hard right now on our manuals to make sure that when you receive your Asimov Here Be Dragon DIY kit, you can actually put it together and get the same working one as we have at our office. Right. So let's go through a bit of what we have here on our docs. So as shown earlier, we also have the manual. So we also have the instruction for the platform side, like our software team, on here also. Okay, but for now, let's go on to Asimov. So as you can see here, we have the overviews of the Asimov manual, right? We have all the specification, right? All the information you would need, of the spec that you might be interesting, such as like squat, bicep curl, lateral raise. We might need to have our Asimov do more leg days, yeah, because his arm is much more developed compared to the legs, right? Yeah. So we also have access to our full BOM list over here. Just put in your email. We'll send you the full BOM list so you can know the cost of the part of everything revolving around Asimov, right? You can build this. You can also decide to build this at home if you would like to. But right now, we are also providing the opportunity for everyone to essentially crowdsource with us, actually. So, right. So we are trying to get everyone to join us to pre-order Asimov so that we can lower the cost of manufacturing. So that everyone can get their hand on Asimov at a low cost, or at the same time getting everyone to join us on the journey to build Asimov together, right? Yeah. Okay. Then also at the same time, we also, as you see here, we have all the preparation steps that you needed to get your tools, mechanicals, electronic preparation, such as your board, your wires, right? And all the software and firmware needed to boot the robot also. All the assembly steps is so neatly labeled over here. Yeah, and so on. Currently in our office right now, we are revamping. We're revamping our manual as we talk at this moment. The whole team is assembling, disassembling, assembling, and then disassembling the robot again to make sure that all of the step is very clearly dictated in the manuals. So make sure that like it's as if you feel like you are building a Legos or IKEA, IKEA furnitures, right? That's kind of like the target we set ourselves, the goal that we kind of want to achieve in the end. So yeah, I'm very excited to soon be able to ship Asimov to you guys, and I would love to get more of your opinions on our manual also, and do join our Discord channel because that's where we actively discuss about how to improve the manual also, and we would love for all of you guys to be a part of it, right? So that's all from my side. Thanks guys for being here. I think for now I can pass it over to Frank next. Yeah.
I think Josh can go next, actually. Josh wanted to add a few things.
Yep. Yeah. So just to show everyone, so hi guys, it's me again. I just want to show exactly how we're going to be refactoring the manual, as Yuki was talking about. So we're going to go for very Lego and IKEA style over here. So currently on our manual, a lot of it is just multiple instructions in a single step, but we feel that we need to be showing what tools we're using and the parts actually being used per step in the manual. We'll also be including a new convention section where we'll show you pictures of each of the motors so that it's easier to map that mental image to the words on the screen. Also, there'll be small tutorials on what a thread locker is, how to use it, how to use an Allen key. It might seem a bit basic for people who've used one before, but after observing members of the team assembling the robot this week, I think it's necessary so that you have a very smooth assembly process. as well as, for certain parts, how you actually attach two things together with multiple screws. You shouldn't tighten them all at once. How to pass wires through, and even how to solder it after you pass the wire in. So this is an example of the level of detail we're going for. We are really writing everything down step by step. The ports of the motor facing your palm. Currently, these are assumptions that we are assuming the user's making, but the goal is to have very detailed pictures and video which accompanies these instructions. And each sub-step will also say what parts you're using for the thing, rather than just having you infer it from the diagram. Yeah, so this is just for the left arm, but this will also be extended to every single part of the rope. On the electronic side, I'm finally done testing the new full spike end board that I've been talking about, I think, for the past 2 or 3 Community Fridays. The PR is in. I will merge this to main once the documentation is done, because a lot of things have changed from the previous iteration. So this will probably go into main on Monday, but the boards are ready for fabrication. So if you guys just go to this branch over here, you can grab everything you need under electrical. The wiring section is also going to get redone because the new boards have resulted in different types of wires, but the good thing is that it's a lot simpler now. And on the motion control side, this image is this DTS file is what you need to actually be able to operate all of the spike end buses. And this has been verified on our robot. I think next will be Frank to talk about our supply chain.
Yeah. And hi all, and it's so nice to meet you here again. In the past 2 weeks, actually, we made a lot of progress in the supply chain here, and I'm so excited to share this program with all of you. In the past week, we already select our CM, and actually we are working with our CM on the deliver service and the final price. And I believe we can share more information with the whole community and soon. And about our building plan, and as I shared the last time, that actually we already kick off the verification building. And now actually everything is on the check, and all of the materials will be ready at the CM side before the 20th July, and our team will be at the CM side to verify all these materials and also do the assembly to make sure these parts meet our quality standard. And also for our first batch building, and it's also ongoing for the moment. The longest lead time and the materials is the actuator, and we already kick off building and in the supply side. So basically, I think we are supposed to get the first batch materials ready at the CM side before the 20th August, and then we are start shipping this all this unit before the end of the August. And also, actually, we are also planning the second batch building, and I will keep updated for the whole community. Yeah, I think that's all update from the supply chain side. If no other questions, pass to Mimi.
Thank you, Frank. I think next we can move on to Ariel, then Alex.
Yeah, sure. Hello, everyone. My name is Ariel, and I'm currently training locomotion policy for Asimov. And let me show you some of the recent update. Yeah. So the previous approach we are trying is a vanilla RL, and the status is that the same and real not currently matches, and the policy can track velocities and handle pushes quite well. But there are a few remaining issues, which is the gate sometimes a bit limping with our previous smaller feet. And another thing is it's sort of hard to control the gates by setting the rewards. And so we're trying some new method, locomotion with motion prior. It's still reinforcement learning based, but it has some help with the motion reference data that you can either feed in your rewards, or you can feed in the critic to make the optimization problem be aware of the imitation data you are feeding. So yeah, the benefit is it learns a very explicit gates from the motion prior data. You can feed whatever data you want, and it's like less hand-tuning words and more controlled gate. But there are some limitations of some of the existing approach. For example, for Beyond Mimic, that requires the imitation data feeding in the observation space, which means you don't actually have control over it, because for currently with vanilla RL, you can set a command velocity to ask the robot to moving like forward or sideways. But with that approach, you can only feed a fixed imitation data, and you just will follow it. And some other method requires very specific imitation data feeding. For example, you have a command velocity at 0.7 meter per second. You have to feed the same imitation data in that speed. So you will have to cover all the ranges of the imitation data with all those directions. And you also need to be very precise about the moment you feed in the imitation data to match with the command velocity. Otherwise, you might confuse the policy. And sometimes imitation data will bias the policy even if you don't want to. For example, it's actually what we've been facing, that initially with the vanilla RL, the robot can like stay the default position when the command velocity is 0. But since we are sort of biasing it with imitation data, it might just like turning its body and stuff to match with the imitation data. And I will share more details how we fixed it. And the approach we selected is called adversarial motion priors. And the benefit of it doesn't require observation with imitation data, and it doesn't need you to cover all like detailed ranges of motions. You just need to cover like rough ranges of all these motions. And it has a motion discriminator to like learn to judge the distribution of the reference data versus your policy, to give you the rewards rather than very explicit like feeding friends. And yeah, this is the pipeline of it and how we generate the motion reference data as well. So we got the motion reference data from Kimodo, and I fed in a few prompts, like a person's walking forward and very speed with like turning left or turning right, or like going backwards and going sideways, and with like swinging its hand, and also like keep the upper body upright. These are the prompts I fed in. And then you will need to do the retarget to azimuth, because this is just simplex format, which I actually share the configurations in the simulation channel and in our Discord. So you have the JSON file for this, and it's basically an IK solver problem, and all this imitation data will be retargeted to azimuth format. And then we have two set of rewards instead of one task rewards. So one set of rewards is what I mentioned from the motion prior, the motion discriminator. So it's basically judge how much your motion transition distribution matches with the reference data, and it will output a rewards based on that. And also the RTG is the task rewards that is basically the same as what we said before. Like if you want to track the velocity given the command, and also some like contact quality, feed sleep, and all these basic rewards, and all this will be like fitting to the policy to be optimized. And you can also set a ratio between these two. For example, you want more like rewards from the imitation data, so the policy will be aware that okay, I will put like more effort into improving this rather than the task rewards. And the ratio we're currently keeping is 0.7 for the task rewards and 0.3 for the imitation rewards. And as for the problem I was mentioning, that it sort of biased the initial frame, it's actually quite easy to solve. I just added a joint deviation penalty when condition on the command velocity equal to 0, so that it will keep the default position when the command velocity is equal to 0. And for like other walking, you can just follow whatever the imitation data is guided it. And also another problem we observe is it's sort of biased by the imitation data. So once you're pushing it, it's sort of using the toe to like recover it. So the easiest solution for this is to train it on slight rough terrain. I can show you here. So that it has to do like much higher lifting its legs to recover from it, and it also improve the push recovery. Yeah, and I can also show you the same results in flat terrain. We can put the velocity higher, and you can see it gets all the styles from the imitation data, like swings, hands, and like the gates are pretty good with like very bigger steps. And also we have some real result here. The command velocity is 0.5. So the step is smaller than if we command to 0.85. Yeah. And I also want to share a bit our next stage of our plan. So we are trying some teleoperation model for Asimov. And here the approach I selected is twist 2. So you basically have a lot of offline data set. You can go to like MS or something and you retarget it to Asimov, and you train a unified tracking policy that takes whatever imitation data as input, and its only task is to following the imitation data. Let me see if I can open this. Okay. Yeah, and here is a sample of it, and we can command it to do like dense motions. It can also be generalized to do like new motions you feed in. And the next motion is dodge. And also you can also command it to do walk, but you won't be as flexible. So you cannot command the velocity and everything. It just follows the imitation data. Yeah, that's all from my end. Thank you, everyone. If you have questions, please drop in a comment, and also let us know if anything we need to improve.
Okay, I think I'm next. Hey everyone, I'm Alex. I'm part of the hardware team, and I'm responsible for the mechanical design of Asimov. So there's something I would like to show you guys today. Mimi, can you help me? Yes. Okay, so well, we basically want Asimov to be anywhere, basically, right? We want it to be very versatile, and we want to have as many Asimovs as possible in any place, in any house, in any factory, right? So one of the decision is adding a platform to it, a wheelbase. So we've been working on this platform for maybe 1 week so far, and the idea is that if you need a robot to do some mostly manipulation task, this is going to be very useful because you forget about all the other caveats of the locomotion and having the legs, right? Since this is part of Asimov, the design concept behind it is very similar. It has to be very easy to assembly. It has to be upgradable, and it has to be quite simple as well in terms of the mechanical complexity of it. Right. So here we have our two wheel. It's basically like a differential transmission, almost like a tank if you think about it. I mentioned is has to be upgradable. So you see there's a bunch of space and a lot of holes here. This is so you can add this like hexagonal rods and start attaching stuff into it. So there's plenty of space for it. It's using this lifter that makes Asimov 1.6 meter tall at the top of the head, and when it goes all the way down, it's around this height. So it's able to pick up any object and put it in the platform, so you can drive away and then put it back in a shelf or something else. Part of the modularity that I'm speaking about is these panels over here are section. So let's say in the future I want to add a LiDAR or cameras here, or I want to actually change the whole back panel for a charging station. It is possible. So let me show you what I'm talking about. So I can just get rid of some of the panels here. You guys can see the very simple structure that holds the platform. So you don't need to like change the whole side panel. So it's basically section. We can remove it, edit it, put whatever sensor, mount whatever sensor we needed, and then just put it back, right? So this is the work that we've been doing, and hopefully we can actually assemble it soon and share more videos of actually Asimov moving around and doing some teleoperation with this. it.
Okay, I think we actually have a lot of questions in the comments. I think there's a few questions for you, Ariel.
Yeah, I think I can answer it right now. Surprising about the progression. Let me Actually, I think the whole progress is quite smooth. There's nothing like really surprising. Oh, okay. Maybe I think of one thing is we found out that once the drawing velocity is slightly higher, the policy becomes a bit jittery, and we still haven't figured out what is the problem to this. But I think we should avoid it. So like, once the drawing velocity is 0.75 rad per second, it starts jittering. But once we reduce it down to 0.4, it stops. Yeah, I guess that's the part of it. And the other surprising, I think, is like when we initially deploy it, and it's very sensitive to the IMU. So anything goes wrong with the IMU, it surprises us. Yeah. If it answers your question. And also, I think there are a few questions from Richard that I think. Oh, sorry. From can I just click it? I think the great solution for teleoperation is actually a neural network that helps to execute rather than just applying the input. Actually, yeah, it is actually. And the policy we are using is just MLP. And applying input just to deliver the intention for it to follow the drawing positions and trajectories. Yeah, but the video I was showing is actually running on Mujoko Wasm, and so it has the physics. It's not, but you just need to give the intention of what you want it to do. Yeah, and yeah, we will be open sourcing, I think, Asimov GMR soon. Doe is also working on it to improving the configuration to make the IK solver better. But yeah, we will open sourcing soon. Yeah, there are some approach that with low body locomotion and simple IK as upper body teleoperation, and actually that's what we are working on right now. So, yep. Let me know if there are more questions.
I think to add on to what Ariel was talking about, I think the main challenge with locomotion was that we actually started from scratch, right? It was a whole new system. The system identification was very difficult. And a problem with a lot of the locomotion material online is that you actually can't replicate it easily unless you have the exact same setup as them. So a lot of the initial time we spent was trying to figure out what actually worked and what didn't. And maybe for some of the things that didn't work, it could just be that it's because of our specific robot. But we spent a lot of time optimizing our firmware and the control loops down there together with our trading environment. I think that helped a lot, especially when transitioning from just legs to a full body. Would Brain Team like to go next? I think starting with Ishni.
No, don't goes first.
All right.
Yeah.
We got more locomotion.
Hello. Okay. Okay. Today I'm sharing about some my experiment on key model, and also with two retargeting methods. So key model is a diffusion model that take the input from the text prompt, for example, a person walk forward or something, and also some constraint. So that is the input of a key model, and it will output the human motion. We have some therefore we have some skeleton from key model, that is Soma human body, SAMPLX human body, and also Unit 3G1 humanoid robot body. So the problem is how can we visualize the motion that is generated from key model
to Asimov robot. So I try a retargeting method first. It means that reusing the key model, existed model, for example, key model Soma RP version 1.1. And then after I got the Soma skeleton motion, retarget it via Soma retargeter. And also, I also try the GMR that is mentioned before, retargeting from SAMPLX skeleton to Asimov skeleton. Okay, so let me give you some experiment from it. We can adjust the time for the action. And for example, we say that we want the motion is the person dance. Okay. And then we click generate. After that, the key model will generate the motion and retarget to Asimov via Soma retargeter. It will take 1 minute for retargeting. Okay, it is ready. And we press space. Yeah, this is some dancing motion. I believe it is a side-by-side move or close side move. Yeah.
This is with a whole body locomotion policy, right?
Yeah.
Yeah. So this is with physics. So it's not. We're not just playing back the action. Yeah.
Yeah. Okay. Let's try another one. Let's try another pipeline. This is SMPLX skeleton retarget via GMR retargeting method. Okay. Load the model again. It will take some time to load the new model. Okay, this is the model is ready, and we actually can we'll have multi-motion. Okay, for example, we say that we need a person pulls the door open. Okay, and the person waves goodbye to behind. Okay, and the person walks away. Okay, right. Okay, let's try generate it. Okay, this is some problem with the axis. I will fix it later. Okay, I think it is some kind of blur. Right. Sorry for that. Okay, this is the motion pull the door open and some waving, yeah, and walks away. Yeah. Okay. We see that when we prompt the person wave goodbye to behind, and then the motion is the robot will turn. The robot will turn their torso, turn his torso, and turn his head to the behind, waving. Yeah. So that's it. That's my so far experiment on key model and retargeting.
Okay, my bad, Richard. I misspoke. The physics is coming. So the next step is actually integrating those work with Ariel's work. And so right now this is not with physics, but the physics is coming very soon. Yeah. Once the retargeter is done, it talks directly to the locomotion policy. Yeah. Okay, so next, I'm going to talk about a new project that Menlo will be working on. Let me share my screen. Okay, so we've just made this repo public. We're calling it the World Encoder. And the reason why we're working on this World Encoder is that we see that for a lot of the models that we would like to train, for example, like a world model or a VLA, we need some way to encode or tokenize our robot sensors, our robot sensor feeds, right? And ideally, what we want to do is at the native sampling rate, so 200 hertz for the motors, and 30 frames per second for the video, and then audio at 16 kilohertz. And what we realize is that what we think really makes sense for us is for an encoder that can take in all of these feeds in a multimodal manner, all of them at the same time. Because on a robot in particular, every one of these feeds are related to each other. The position of the motors on the robot, because they are on the same robot, affect the view of the camera, right? So the encoding of vision should be kind of related to what the robot is currently doing. And one very kind of way to understand this is for example, if you're trying to pour water into an opaque cup, right? Like a water bottle like this, you would actually use your sense of hearing rather than your sense of sight, because like a human wouldn't, wouldn't look down from the top of the cup, right, and try to pour water. You just hear the sound, and as the water bottle gets filled up, you can just hear the frequency. It's very easy, right? But then again, if you close your eyes, you wouldn't know where to aim your water bottle. So then you would need both, like on a normal robot to do something as basic as this. You would need both of these sensors, right? And so it just kind of makes sense that like all of the sensors on the robot together construct a more holistic view of the world than each of these sensors alone, right? And at the end of the day, like how well we do the encoding affects how well we can do in the downstream model, right? So what we want to do is run run experiments to try to see if we can improve, based on our knowledge of Asimov, right? The way that we encode information into our downstream models, right? And there have been some previous work like this, right? Where, like on robot arms like this, you get acoustic data, visual data. In this case, it's tactile data, but motor data can also give us some of this information. But the idea is, of kind of multi-sensory inputs into models is not new, right? So what are some of the difficulties with doing this, right? Is that all of these data have different sampling rates, right? 16 kilohertz audio, 200 hertz motor control, and then 30 hertz video, right? It's actually the matrix is not very square, so it doesn't lend itself well to putting it into a transformer, right? So actually we're leaning back onto this old paper, Perceiver IO, that solved this problem many years ago already, on the use case of StarCraft, right? When back in the day, when I first got excited in AI, was actually when the StarCraft model came out. Like you got your mouse, keyboard, you got your video stream, you got the audio. All of these are like very multimodal, and we were already back in 2022 able to train a model that can take in all of this multi-sensory data, right? So we're just adapting this to kind of robot data, right? So these are some of the examples of the kind of data that was required to play StarCraft 2 back in 2022, right? And this was also in a different era of compute, right? We had much less compute in 2022 than we do today, right? And of course, to train this encoder, we're using the new self-supervised learning because for encoders, we want to lean on self-supervised learning so that we don't need labeled data. Because the encoder needs to be general enough that we can use it for all kinds of downstream tasks. And kind of like the latest kind of most promising approach right now seems indeed to be JEPA, the joint embedding predictive architecture, right? But on a robot, we do have to kind of rethink a little bit of how we do JEPA. JEPA being like the overall architecture where you have an encoder, right, for X and a Y, right? And the X and Y can be in both space and time, right? For a robot, like the perhaps the time and space need to be treated slightly differently from just pure images, right? Because all of our sensory data has huge element of it's actually signal processing. It's huge element of time in it. So we will be making some modifications to the encoder, right? Using kind of the perceiver approach to kind of map all of these different sampling rates of all of our sensors, right? And the predictor network is a very efficient way for us to basically train this encoder in a self-supervised manner, right? And we do have we have been looking at LeJepa for kind of a good loss function, and I think later on Ishneet will share more about our experiments using the LeJepa framework to do the model training. For the robotics dataset, we're starting with this dataset called RH20T, which has all of the interesting data at the different frequencies. So it exposes the kind of problem that we're trying to solve, right? There are actually a lot of robotics data sets out there that remap everything to the same frequency, which is very good for like downstream model training, but doesn't suit our purpose. And actually, this was one of the only data sets we could find of a sufficient size that had this detailed like frequency information and of the range of modalities that we care about. So we're starting with the RH20T dataset and the LeJepa training framework, and the data size of this model is actually pretty huge, for at least for our resources, and we're training in public, right? So we're sharing updates on our repo here, our roadmap for each of these projects. We also have a project that's upcoming. We can share more next week on the VLA model. So VLA model will be coming, both like the traditional VLA and a VLA based on this new world tokenizer, right? And some of the experiment results, I think Ishneet can share with everybody. We have some early interesting results, but we're waiting to scale, and I think Ishneet can share more. Ishneet? Okay, Ishneet having some mic issues at the moment. Please hold on. Ishneet, yeah, you have. Maybe I can just share first, and then Ishneet can jump in. Yeah, Ishneet, jump in when you get the mic done. Let me share my screen first. Okay, so let me share the experiments, right? So these are all experiments that have been done by Ishneet. So the credit goes to Ishneet. Okay, so first of all, what we did was we tried training LeJepa, just the basic framework, right? We're using a VIT V2 encoder for all the image frames. So we still rely on a little bit of pre-training, but what we're trying to do is just to show that kind of like the LeJepa model and the training framework works on a robotics data set. So we chose like kind of like the smallest RH20T config. So the CFG3 stands for config. And we trained it on that. And at the start we used like too high of a learning rate, and then lowering the learning rate fixes it. So we've been able to show, that we get this improvement in the metric, right? So at some point this converges because this isn't a huge amount of data, right? So then the next thing we want to try is, so this was video only on config tree, right? And then the next experiment we tried was actually the more interesting one, which is, can we use the robot state to improve the performance of the video encoder, right? So we use both video and robot state to improve the performance, right? And what we've done is actually write a new encoder using the perceiver architecture. You can see all of this. So we will clean up the code in due time. So if you look in, you can find the architecture for how we did this. But what we managed to find is that, yeah, indeed, like the R-squared value for perceiver, right, in terms of like the encoder is better than just raw vision, right, and also better than the LeGepa vision with some control for, like, I think the embedding size, so that, you know, the numbers make sense because of the because of the number of embeddings. Yeah. So this is very promising, right? And I think our next step right now is to scale up the training with the new with the rest of the RH20T data set, and I think we will be able to share more experimental results next week. Yeah.
Okay, today's session is running a bit long because we've been so excited to share with you everything that's going on behind the scenes for us. I think as a final segment, can I ask Herman to do the promo, please?
Hi everyone, so I'm Herman here, HR of Menlo Research. Very nice to meet all of you. So I just wanted to let you guys know that we have lots of new roles opened up on our page, and we even have our internship program opened up right now. So for those who are based out of Singapore, Ho Chi Minh, and even potentially San Fran in the future, you can apply for our Menlo Ambassadors program. So we look forward to talking to you guys, and yeah, I look forward to meeting all of you as well. See you.
Sorry, I just realized I was on mute. But all right, I think that's everything we've got for you today. Thank you all so much for joining us, whether you caught us live or you're watching this later. We really appreciate you being here. If you enjoyed this call, the best thing you can do is make sure you're following us on X, join our Discord if you haven't already, and that's where a lot of the day-to-day happens between these calls, and subscribe to our YouTube so you never miss out on any one of these sessions. And I think just to wrap it up with the shipping news we shared today, this is honestly such an exciting time to be a part of our community. So we'd love for you to be right there with us as it happens. And thank you again for being here, for your questions, for all of your comments. We apologize if we weren't able to get to your specific question. But yeah, we'll see you at the next one. Thank you. I think that's a wrap.